Before we go further to the last topic in this chapter, let's have a look at this one first. So you have two types here. One is your gasoline engine or your spark ignition, and the other one is your diesel engine or your compression ignition type. So if you plot this spark ignition PV diagram, so you will see that your heat addition is happening at constant volume. So you have, this is your 1, this is your 2. So this is the heat addition process, and the last one is your heat rejection. And if you have a look at your compression ignition PV diagram, you will have heat addition over here and heat rejection over here. So if we label all these things, and finally you can see that your heat addition is happening at constant pressure and your heat rejection is happening at constant volume. Alright, now you will have another cycle, which is actually the combination of these two, and we name it as a dual cycle, where in dual cycle, as the name implies, it's going to make use your spark ignition and your compression ignition. So you have two times heat addition, which is happening in between 2 to 3 and 3 to 4, and the heat rejection will be 5 to 1. So if you can see here, in a spark ignition system, the heat addition is happening at constant volume, while the diesel engine or compression ignition, the heat addition is happening at constant pressure. But when you have a dual cycle over here, now your heat addition will be in constant volume and also in constant pressure. Now that we have a dual combustion engine cycle, which is operating at higher speed, because you have two times heat addition over here. One is at constant volume and the other one is at constant pressure. So when you wanted to analyze the thermal cycle efficiency, it is the same thing, which is 1 minus Q out over Q in. But now that you have Q in two system, one is at constant volume heat addition, where you have state 3 and 2, and the other one is constant volume constant pressure heat addition, which is in between state 4 to 3. And your heat rejection is still at constant volume. And if you have seen the cycle in a previous video, you will understand the sequence of this heat addition. You have another term introduced here, which is your epsilon, or in other words, it is actually the ratio between P3 and P2, because sometimes the question may ask you what is the pressure at 3. So we represent it as epsilon, and by using the ideal gas relation, you can substitute these terms into your T2 over T1, V2 over V1, and rearrange into this thing, and finally you will have this thermal cycle efficiency. But however, it is much easier for you to analyze one by one, which is you make use of this Q in, and then you calculate for your Q out, and then you substitute into your thermal cycle efficiency. So we recap back what we have learned. Number one, we have your spark ignition engine, and it works under constant volume. Number 2, we have compression ignition, where it works, the heat addition works under constant pressure. And finally, you have a dual cycle, which your Q in is the addition of your constant volume and your constant pressure. That's all for this chapter. Hope that you gain something from this, and thank you.